So welcome back. A very short video looking at the main points of chapter 13, Simple Linear Regression. Although this chapter is long and quite involved, lots of equations and lots of things to put into place, the main objective of the chapter is to build a model that can describe, predict, and control the dependent variable based on an independent variable. So what are the dependent and independent variables? The dependent variable is a variable that we wish to understand, and the independent variable is the variable we will use in order to understand that dependent variable. So there is a general equation discussed here. The general equation says that y is predicted by an intercept plus some slope and an error term. The error term is described by this variable here called epsilon. Of course, because this is the general regression equation, it comes from a population. Population is not usually observed. We will estimate these coefficients, and the estimated equation will look something like this. Y is equal to little b0 plus b1x. Sometimes, or oftentimes, you will see this with a little hat. The hat stands for estimation. A few assumptions that you need to keep in mind when you are running a regression equation for the benefit of the exam plus your professional careers as well. The first assumption is that the error terms will have an average of 0. The reason being is if they don't have an average of 0, if they have an average of, let's say, 1 or 2 or some positive or negative number, that's a trend. And once you know the trend, you can correct for that trend. So, for example, if a car is drifting to the left, and you know that it drifts to the left, you will correct it and turn the steering wheel to the right in order to put the car back on the right path. So the average of all the error terms should be 0. Second assumption, all the error terms have a constant variance, meaning the level of error doesn't change as y changes or as x changes. So that is an important assumption. The consistency of the error terms is very much paramount. Part 3, or the third assumption, the normality assumption. The error terms are distributed around the estimation line in a normal fashion. So an illustration right here, you can see that this is the estimation line. I'll highlight it here like this. I'll just maybe use a red line. So this is the estimation, and you can see here and here the error terms are supposed to be normally distributed around that line. This is important in order for the equation to be consistent across the prediction intervals. And finally, the last part, the fourth assumption, the independence assumption. All the error terms are independent of each other. It means that once there's an error, the following error is not related to that error at all, and so they are randomly distributed around the prediction, and so they are independent. Sometimes on exams, these are often asked in some way, shape, or form. Please keep these in mind. I took the time to just list the equations. I'm not going to discuss them in this video because I feel like that's a little redundant, especially since we're going to cover them in an example. Two very, very, very important concepts to look at: the correlation coefficient and the coefficient of determination. We'll start off with the correlation coefficient. It's called rho. Often you see it as R. It gives you the strength and the direction of the relationship between X and Y. So this chart right here, a correlation that is seemingly like this or this is a perfect correlation. It means that X and Y move in a certain way consistently. Something like this is a strong positive relationship. There is a pattern, it's trending upwards, but there is some variation, and also this is a relatively strong negative relationship, meaning as X changes positively, Y changes negatively, and vice versa. and so the relationship goes in opposite directions. That's correlation. And finally, something like this, there is no correlation because there's no pattern. So correlation coefficient, it's represented by the Greek letter rho. It looks like P. Often in Latin letters, we write it as R. It's a number between -1 and +1. It has no units. Make sure to write that. So no units. It's not in percent. It's not in meters or feet or pounds or kilograms or anything. It's simply a measure, a relative measure. The closer it is to 1 or -1, the stronger the relationship. The closer it is to 0, the less strong the relationship. The sign of R is the same sign as the slope of the equation, which we'll do an example of. So if the slope is positive, then R is positive, and if the slope is negative, then R is negative. It goes without saying. Second, another important concept is rho squared or R squared. It basically answers the question, how much of the movement of Y has been explained by X? So we're using X to understand Y or the movement of Y. So R squared is essentially a measure of how well we did. It's a value between 0 and 1. And this one does have units. Sometimes you can translate it as a percent. So 0.76. If that's your R squared, it means 76% of the movement of Y has been explained by X. In order to calculate R squared, it is a ratio of SSR over SST. SSR is called the explained variation. The equation is right here. So it is the difference between predicted and average. And the denominator is SST, which is total variation. It is the sum of explained and unexplained variation. Finally, a few side notes. The mean square error. This is the standard deviation. In this case, it's the variance of the error terms. If you take the square root, it becomes the standard error. It is the standard deviation of the error terms. You can derive it using this formula, SSE divided by n minus 2. SST is the unexplained variation in the regression equation. Essentially, it is the difference between actual observed Y, so actual yi, and this is the predicted y. So you get this from the equation. So y hat is equal to b0 plus b1x. So that's how you calculate the standard deviation of the error terms. I will stop right here for now, and I will create another video for the second half of the chapter in order not to make these videos very long.